Let's see. Please move this window. What does that mean? Okay, so I just what'll appear is just like me writing my notes and anything I say. Um, so that doesn't mean that you can't that you should stay home and not come to class, because I consider it pretty important to come to class. You get to ask questions, you get to do the activities and talk to your fellow students, stuff like that. I think relationships are very important. I want to tell you who I am. I'm Laura Cooley, and I've been at Rhode Island College quite a long time, and I actually really love it here. Some of you, I hope, are excited to come to chemistry class. How many of you had chemistry in high school? Good. Okay, great. But that doesn't mean you have to have had chemistry in high school, because we do start from the beginning. I hope that you're more excited than scared, because, I understand there's a little trepidation with chemistry sometimes. But I hope that I can help all of you become good students, great students of chemistry. And I really want to emphasize that you should not be a stranger. Unfortunately, my office is not in this building. My office is in building 2, which is, I believe it's the next building next to the financial aid office. So it's on the East Campus. And I'm at, I think I'm room 109. I just moved there, so I'm pretty sure it's all the way down the hall on the right. And, I'm around quite a bit. I actually like my office. It's kind of nicer than the old office, which brings me to the next thing I was going to say, which is that the physical science department is pretty displaced right now. I don't know if you know, but we're getting a new building, which won't be ready for a couple of years. So we are supposed to have temporary lab space in Whipple for the general chem labs, but unfortunately it's not ready. So it'll probably be ready in September. So right now the lab is going to be meeting in Craig Lee 213. So that's where you should go, even though it says Whipple. I don't know, I think it says Whipple in my Rick, but that's wrong. It's Craig Lee 213. Okay. So anyway, I know it's a little out of the way to go to my office, but I really am able to help you with a lot of things, and I'm pretty nice. I'm old, I know, so whatever. I'm like your parents or older, but I really want to help students, and so I hope that you can avail yourselves of that as something, if you need help with something and you want to come and see me, that would be great. Okay. So I want to tell you that I've given you the syllabus. There's actually two syllabi in a way that I've handed out. There's a syllabus that has a lot of information on it that looks kind of like this. Okay. So I've given this to you, and I'm going to sort of notate some things in it. I don't have time to go over this whole thing because we're going to do chemistry very soon. But if you have a pen, which you should have, take out this copy of the syllabus. I want to point out that I use Blackboard. I use that mainly for posting things. I have a problem set that for every chapter that you'll be doing on Blackboard. So you should make sure you check Blackboard pretty often. I already told you the lab is in Craig Lee 213 for now. There are 3 sections, as you know. The lab packet, the first handouts will be given in the lab, so you don't have to worry about that. They'll tell you all about that. The text that we're using is an open source textbook. We call it OpenStax. Well, that's what it's called. It's the Chemistry 2E. It's not the Atoms First. But anyway, it's free. It's online. You can print a PDF of each chapter. The bookstore is supposed to have a PDF of the whole thing, but I don't really recommend that. That's a giant thing to carry around. I think it may be better to just read it online. But anyway, that's what we're using. I do want to say a few about a calculator that first of all, you should bring it every day. I mean, I know that when we do problems in class, it's possible to use your phone. But you can't use your phone on a quiz or an exam. In fact, you have to put your phones away. So what's the point of learning how to do calculations on your phone when you're going to have to use a calculator? And anyway, phones are often difficult because sometimes it's hard to use scientific notation or something. You know, you have to get a calculator, and the calculator has to be able to do scientific notation, and you have to bring it to class because we do problems in class. And you should, I don't know if you have a calculator with you, check and see if it has an EE key or an EXP key, because that's something that even next class we're going to be using, and you should make sure that you bring it, and I'll try to show you what to do with this key. It also, if you're going to take 104, you really should get one that has logs and natural logs, but that's really for next semester, not this semester. Okay. I want to just mention, let's see, that at the end of this syllabus, there's something about academic honesty that you're going to need to read and sign. So it's all about, you know, what that means here at Rhode Island College. And it goes on. This is not the whole thing. It's a page long. And what I would like you to do is next time when you come to class to put your name, print your name, and sign it and date it. And you basically, in doing that, you're promising that you will abide by this policy. And that's kind of important, you know, to do your own work. Okay. Other things, there are extra credit opportunities in this class. And there are two ways of getting extra credit. One is by getting something I call a gotcha slip. That's like, I gotcha. That's when you catch me in a mistake. And I do make mistakes, and I get kind of grumpy when you catch me in them, but that's all right. Don't worry about it. It passes. So if I make a mathematical mistake, or I say something that's incorrect, either in class or if you catch something on an assignment or a quiz or a exam, you know, I will give you a gotcha slip. And I'll explain what this means in a little bit. You get 2 special problem points for pointing out the error. Okay. And you can collect these slips, and at the end of the semester, you give them to me, and I use them to calculate extra credit. Now, what is a special problem point? So there's different ways of getting these points. I have special problems that I grade. I grade them on a scale of 1. So if you get a 0.9, it's like getting a 90. And what they do is they add up, and at the end of the semester, this is an explanation of how they add up to give you extra credit. Basically, say you get 20 special problem points during the semester. That gives you 20% of the difference between your grade and 100. And you can see I do some calculations here, some examples, so you can read through that in the syllabus. But anyway, that's a nice form of extra credit. And you could get it, like I said, by either finding a mistake that I make or doing these special problems. So I recommend that you do all the special problems, because you never get, it doesn't hurt you in any way. It only adds to your grade. It doesn't take away from it. And also, you have to know how to do those problems anyway. So, you know, they're really good. I do have stuff in the syllabus about grading. You could see that I have 3 exams and I have a final, and none of the exams are more than 11%. So they're not, you know, like big chunks. I do have these online problem sets that you should be able to get these all right, I would hope. 1 every chapter. And I have something called the handout of the day. Okay. And you see that one of the pages I gave you is called handout of the day. And so basically, this is a way of giving credit for coming to class. And basically, it's some exercises that we've covered during class. It might be long, it might be short. Today, it's, you know, anyway, we'll see. But anyway, when you do it, basically, just for handing it in, you get 3/4 of the credit. See, I graded on a 4-point scale, and you get a 3. just for handing it in with an attempt. Okay, so if you get a 3, it's not very good, right? You might have done something wrong. If you get a 3.5, that's like getting half credit, really, but you'll get 3.5 out of 4, which is, 3 out of 4 is a 75. So that's not bad for not getting it right at all. And a lot of people, most of the time, people get 4s, 3.9s, things like that. So, but you have to actually come to class to hand that in. So I won't accept handouts of the day after. That's not, I won't do that. But I do have a couple of drops. So it's like if you get sick, it's not really a problem. All right, so that's how that works. This is kind of a rough outline of what we cover when and when the exams are. But that's why I have this other syllabus part 2, okay? Because this gives you more details about what we cover, and it tells you when we have a quiz or when we have an exam. This is tentative, these dates of quizzes and such. They may have to be changed, but I would give you plenty of advance warning for that. So I'm going to start right in with some chemistry. This is what I have. I would like you to interrupt me if you have a question. You just raise your hand. You don't have to shout. That would be kind of bad, but just raise your hand and I'll try to answer it like as we go along. If you don't understand something, I like this to be a little bit back and forth. I know it's a lecture class and most of the time we're doing lecture, although today I plan to do 4 different activity sheets that are all part of the packet, which is the other thing I wanted to tell you is that we have these packets, right? This is a packet for chapter 1. So you should bring this every day too. It's got, in the packet, I have some figures. When I talk about things that have pictures, I want to give you a copy so that you can write some notes next to the picture. So, you can have a better idea of what I actually covered in class about those pictures. So I'm going to do this with every chapter. So this is chapter 1. And there's activity sheets in there, and we'll hopefully get through 4 of them today. Okay, so anybody got a question to start out? Yes. What do they do? Oh, they're not due. I don't collect those activities unless they are special problems, in which case they're extra credit. And as you can see, if you look at the handout, take a look at the handout of the day, you'll notice that there are 2 problems on there that come from the activity sheets. So some of the activities could be part of handout of the day. But it's not like you have to do this whole packet and hand it in. We're going to do it as we go through the chapter. Most of those activities, I would venture to say probably all of them, for the most part, we'll do to some extent in class. And everything that we don't finish in class, you finish at home. But I don't collect the homework. I mean, I don't collect the packets. It's not like that. It's for you. And I post the solutions. So, after we do it in class, or after it's due, if I assign it as a special problem, I will post it on Blackboard. I use Blackboard a lot for that sort of thing. I don't use it much for posting grades and things like that. Maybe I will this semester, but I'm not sure. Any other questions? That was a great question, by the way. And so if you have a question, probably everyone else has the same question too. So yes. If you don't post on Blackboard, what? Oh, well, I give you back your stuff with the grades. Yeah. Right. I might think about that this semester. Students probably love that. All right. Anything else before I start? All right. Well, if you have another question, you need to ask me. Okay. So now let's do this. Okay. All right. So I'm going to start in the section 1.1 of our OpenStax book is really just a lot of introductory stuff. It's very short. So we're going to start with 1.2, which is atoms and molecules. And it's really just an introduction today. Where we really study atoms and molecules is in a later chapter 2. So today it's just a few words, get you started. And so atoms and molecules, these are the basic building blocks of all the stuff all the stuff in the entire world and in the entire universe. Does anyone know what we call the stuff of the world in a chemistry class? That's right, stuff. Stuff is matter. I don't use that word a lot, but that's a word that you should know. Now, matter obviously, it can be simple or it can be very complex. But the simplest substances, the simplest forms of matter, anybody know what they are? Elements, yes. And this being a biology lab building, not a chemistry building, there's no periodic table on the wall. I'm gonna have to try to fix that. But anyway, elements are the simplest forms of matter, and the smallest unit of an element is what? Smallest unit is an atom. Yes, an atom. Okay. And all the elements are listed. Oh my gosh. I have a big space here. Oh, I thought I was going to take up that space. But anyway, all the elements are listed on this, the periodic table. Okay. Now, don't memorize the periodic table, please. It would take forever. I couldn't possibly. I would be so bored. However, you do need to know the names and the formulas of elements that we use a lot. And those are checked. See these checks? You have a copy of this. Look at your copy. And you can see you have a copy of this periodic table with check marks on quite a few of the elements. You can see there's a lot that are left out in the middle and the bottom. And what I'd like you to do for these checked ones is to know the names and the symbols of the checked elements. And I'd like you to do that by September 7th. Okay, because we have our first quiz, I believe, that day. Okay, so some of these are pretty easy. H, hydrogen, things like that. Some of them really make sense. Pick that up. So hydrogen, some are like chlorine, CHLORINE. Sulfur, this is just some examples of the checked elements, some magnesium. And now these make sense, right? Magnesium, here's the M, here's the G, here's the S, Cl. So element, as you probably know already, element symbols are either one letter, which is capital if it's one, or two letters where the first is capital and the second is lowercase, like Cl. Okay, but then we have some tricky ones that they throw in there just to make us crazy, like mercury and iron. Okay, and now why would you have Hg for mercury? It comes from the Latin. I don't know how to say mercury in Latin, but it must have something to do with Hg. Fe, I know that's like ferrous or ferric, or that means that's what iron in Latin. So some of them are a little bit harder, take a little longer to memorize, but you know, I think it's pretty doable. So that's my basic introduction to atoms. But we also have another simple form of matter, and that happens when you have atoms, a few atoms or more atoms joining to make what we call molecules. So molecules are two or more atoms that are bonded together. And we call the bonding, we call them covalent bonds. And this is not the day where we're going to talk about bonding. Bonding is a chapter 8 topic. So that's the last chapter that we do this semester. So you can just think of these bonds as forces holding these atoms together. Pretty strong forces we call covalent bonds. All right. Now, when you have a molecule, you have a formula. For example, H2O. What does that mean? the formula just represents a water molecule. And what it means is that every water molecule has 2 hydrogen atoms. So the subscript here is a 2. And now here you have no subscript. When you have no subscript, it means 1. So it has 1 O atom. So you have 2 H's and 1 O in 1 H2O molecule. I would hope that many of you already know all that, but if you don't, there it is. Another example, here's NH3, 1 nitrogen atom, 3 hydrogen atoms in 1 NH3 molecule. Okay. I wonder if this is still being recorded or not, because it doesn't. Let's see, just checking. Well, I don't know. We'll have to see later. Okay. Now, a molecule is the smallest unit of what we call a compound. All right, that's the next level up of complexity. So molecules are the smallest units in compounds. And when you have a compound, there can be different ways of representing that compound. And I just told you about the formula, that H2O over there, that's the formula. But there are other ways of representing the compound. This is also something I've given out, so you could see it on your sheet of slides. And if you want to make any notes on there, go ahead. So there are different ways of representing a molecule. This one gives a structure. This is like a structural formula. And by the simplest model, you just put the letter and you have lines that represent the bond. So this would be a bond. And another way of doing it that you see oftentimes in pictures in books and things like that are what we call the ball and stick model, where you represent atoms by balls and bonds by sticks, which is really not a very correct representation, but it works for us, you know. Another one we call the space filling model, and this kind of shows more the electron cloud, which is more correct, although it shows it as being very finite. And what this does is it gives you an idea of the sizes and the overlaps of the electron cloud. So really you have an overlap of the electron cloud of the hydrogen and overlapping with the oxygen. So this gives you more of an idea of what the shape of the molecule kind of looks like. So these are very simple. It's a very simple molecule, obviously H2O. And just to show you what chemistry can do, as you, I'm sure, know, there's DNA. I should have asked you what you think this was, but this is a sample of DNA. And you could see that this is really the ball and stick model here. Okay. And the one on the right is what it would look like with space filling models. Okay. So this is a much more complex molecule. And so, you know, in Chem 103, we don't go from, 0 to 100 miles an hour in the first class. We don't talk about DNA. We start with the simplest things first. We take it one step at a time. All right. So that's what we're all about here. So that's just a little quick introduction to atoms and molecules. What comes next in the book is how science is done. They talk a little bit about what we call the scientific method. And I have a lot to tell you about this. So this is scientific method. And by the way, does anybody know, okay, when scientists try to figure out something, they go into a laboratory, let's say, and they use the scientific method, but does anyone know what is the word for what a scientist does in the lab in order to do that? Experiment, yep, but it's all part of research, right? So research is how we term, scientists discovering things, whether it's in the lab or you could be out in the field or something like that. Now, when you use the term research in high school, mostly teachers are referring to library research, where you go and you look things up in books and and you, write a paper, let's say a research paper about a topic. Now, when you do scientific research, you have to start by going to the library, or it's all online now, okay? You could do your research online, of course, but that's just the beginning. That would be to figure out what other scientists have done on that topic. Scientific research, though, is something that has to be done in a lab, in a sort of a lab setting of some kind. We're not talking about library research. It really starts with making observations. And there's all kinds of things you have to be careful of, like doing experiments that are controlled and things like that. I'm not really going to talk about the details of it. But what you do is you observe an experiment in a lab or in a natural setting, for example, and this leads to what we call data. And I do want to talk a little bit about data and what it means, okay? Now, when you think of data, what comes to mind? I don't know. Information. What sort of information, really? Numbers. Okay, that's right. So most of the time, data is associated with numbers. But I'm here to tell you that data, of course, does not have to be numbers, right? Numbers is only part of it. And also, not all numbers are data. And so I actually am going to go over an activity with you that tries to get you to understand the difference between data and other numbers, all right? So it's associated usually with numbers, but data can be descriptive. It could be words. It could be what happens when you react hydrogen with oxygen. It could be a description of there's an explosion and heat is released, things like that. That's also data. So data is really not just numbers. It can be descriptive, and it also can be measurements. Like numbers are involved, which involve numbers. So when you have descriptive data, we call that qualitative. And numbers is quantitative. Okay, and this is where research starts, with observations, with make descriptions, making measurements, things like that. So what I want to do is let's go to the first activity, and that's this one here. So basically in this activity, I go over what I just said. So scientists refer to observations as data. Oh yeah, here's the fun fact. Data is actually plural. The singular is datum, okay? So that's right. We always say data, no matter whether it's plural or whatever, but that's the official thing. It could be qualitative or quantitative. So what I want to do is go through some statements, and I better amend this one because it is simply false. Let's make it cloudy. Okay, because it is cloudy today. So let's look at this statement. Statement 1, the sky is cloudy today. So what is that, an observation? Yes, so that's an observation. So that is data. Is it qualitative or quantitative? Qualitative. Okay, good. Okay, here's one. When vinegar is mixed with solid calcium carbonate, bubbles are produced. So what is that? Is that data? It's a description, right? It's a description of something you saw, or that's right. You mix vinegar with calcium carbonate, bubbles are seen. That is an observation. So it's data. So this is an observation, and it is data. It's qualitative. I'm just going to write qual there because it's not, doesn't involve numbers. Now, what about this third one? When vinegar is mixed with solid calcium carbonate, carbon dioxide gas is formed. Is that an observation? does that carbon dioxide molecule hold up a sign that you could read that says, I am carbon dioxide now? Right? So that is not something that's an observation. The fact that there's a conclusion there, right? That carbon dioxide is produced. Yes, it's true. Carbon dioxide is produced, but you didn't get that just from observing that reaction. You got that by analyzing that reaction, by knowing some theory, right? You had to know, from what's reacting that you would get CO2 because somebody developed a theory that allowed you to make that conclusion. So what's very important that to understand the difference here, okay? So this is really an interpretation, right? The molecules don't hold up signs saying they are CO2, carbon dioxide. So you didn't get that by observing. This is an interpretation that uses theory. Do you have a question about that? I'd love to answer it if you do. Does that make sense? No? Yes? Okay. All right. So let me ask you guys to do these next ones. So you do these. And actually, you could continue if you have time, because I'm going to stop at some point and go over them. But do those, and if you have time, do those. I'm going to just give you a few minutes. And I'll walk around, and if you have a question, you can ask me. And I'm happy to have you talking. So you can get in the habit of sitting next to people that you like to work with. I know it's like the all. That's actually. How do you find? All right, let's go over some of these. We answered some questions. Okay, what about when 2 grams of aluminum is burned? The mass after burning is 3.78. What is this? So these numbers here, yes, this is data, because this is something you took it, you put it on the scale, you observed, the scale said 2 grams, you did the burning, brought it back, and it was 3.78 grams. So these are observed numerical data, they're quantitative. Anybody have an idea of why the mass actually went up when you burned it? Yes. I can't hear you, sorry. Yes, the aluminum picked up oxygen from the air and formed aluminum oxide. So it actually had more matter at the end than it had at the beginning. But it didn't come from nowhere, right? It came from the oxygen, but that's for another day. Okay, when aluminum burns, it produces a white substance. The white substance actually is aluminum oxide. But in any case, that's not what all you can see is that the substance became white. It produced a white substance. So that is an observation. So that is data, and it's qualitative. Qualitative. Now, here again, just like in the example with the carbon dioxide above, okay, when aluminum burns, it produces aluminum oxide. That is an interpretation. You have to know that when aluminum reacts with oxygen, it produces an aluminum oxide. That's based on theories of chemistry that are not just from that observation. It doesn't hold up a sign and say, I'm aluminum oxide. No, it doesn't work that way. So this is not data, because this involves interpretation. Okay. All right. Now, the mass of a solid block of lead is 455 grams. You put it on the scale, you measure it. This is a quantitative piece of data. Again, here you take a ruler and you do 3 different measurements of the length, width, and height of a block of lead. And then you go wash your hands because you don't want to feed a small child after you do that, or even yourself. But anyway, so these are also data. They are quantitative data. Okay, but now, what about this? What about this one? Is that data? Why? There's a computation involved. You had to take the length and multiply it by the width and multiply it by the height. Okay, so you have 2.54 centimeters, and that's what the volume equals, just to finish my thought there. 2.54 centimeters times 3.75 times 4.21. And when you do that, you get, what do you get? What did it say? 40.1. And you notice you have centimeters, centimeters, centimeters. That's centimeters cubed. Anybody know what 1 cubic centimeter is often called? 1 milliliter. Okay, so that's just, it's basically a centimeter on each side. That volume, a little box with a centimeter on each side, is a milliliter. But that's for another, that's for later. What about this? The density. Does anybody know what density equals? It's the mass over the volume. So again, this number here that you get, 11.3 grams, that's mass, over cubic centimeters, that's volume. You had to do a calculation to get that number. So even though it looks numerical, it is numerical, it is not considered data. Okay, so this would be, what was the mass? 455 grams divided by 40.1 cubic centimeters. So that comes out to 11.3 grams per cubic centimeter. So this involved a calculation. So it is not data. Okay, that calculation somehow mathematically interprets the data of the mass and the volume to give you a density. Okay, here's another one. So I live 2.1 miles from the Clark Sciences building, which is being torn down now, well, kind of little by little. But in any case, that's something that I could observe by looking at my odometer. But actually, I guess I could take my odometer, the trip thing, and zero it, and then drive to work, and then look at the thing, and it says 2.1 miles. So that is an observation. So it's quantitative data. What about this one? Yes, I could start a stopwatch and ride to work. So that's based on an observation, like a stopwatch. So this is also quantitative data. And what about this? Yes. Yeah, I mean, that 2.1 miles, like, for example, if I wrote down that the odometer was, 3,402, and then it went up to 3,422.1. Oh, no, yeah, no, geez, whatever, 3,404.1, then I could subtract, right? And that the data would actually be what the odometer readings were. And then like I said, I could come up with a way that actually get that to be by using the trip thing. Yeah, so I guess you're right about that, but sometimes, depending. But there's no question here that this is not data, because in order to get this, you would have to divide, you would have to calculate the speed, right? And the speed is the distance over the time. Okay, so first I would probably take my 4 minutes and 30 seconds, and I would convert it all to minutes. And then I would convert from minutes to hours. So those are calculations, right? And then I would take the distance being 2.1 miles. The time is 0.0750 hours. And that would give me the 28 miles per hour. Okay, so yeah. So that's not data. But here we have a picture, and presumably what I'm assuming here is that, okay, so we have a syringe, and I'm holding the syringe on one side with my finger, and I'm pushing in, and I could see that the volume here in the syringe, I can read it, 5, 10, 15, 20, 25 milliliters. So that's the volume in here. And I could also read, this is showing that there's a pressure gauge. So that is an observation made based on this instrumentation. And here's the number. Okay, so these are both quantitative data. Okay, so anyway, in science and in chemistry class, and you do have a lab, we will be having actual labs later on after the first couple of weeks, I hope, that we distinguish data versus results. So in lab, we pay attention to what's data and what's not data. Like I said, data are observations. The things you observe them directly. That's, I mean by like raw data. It's what the measurement is telling you, what the observation says. The sky is blue today. The length of the block is 2 centimeters or whatever it is. Results involve some sort of analysis of data. So you can do calculations to get results. Those results are not data. Okay, so for example, the volume is 40.1 of that block that we talked about in activity 1. So it's using data, but it's not itself data. All right. Now, I tell you this because in lab, we do make a distinction between data and results. And a lot of times students think that all numerical anything that they write down in their lab report is data. But I hope that after doing this exercise, you realize that that's really not true, that the only things that are data are the things that you have measured and observed. Okay, and we have something in lab, we have a data sheet where you keep track of the data. So you don't write the results on the data. So we make a distinction between results and data. When you have data, we're very careful to record it in pen. Why do we record it in pen? It's because we don't want it to be erased. And when you're doing a chemistry lab in college, it really doesn't matter if, you write something down and you erase it, but we're trying to train you to actually be sort of science professionals. And when you work in a professional lab, you write down some data, you can't erase it, because you didn't like the result. You didn't like it for some reason. So we do this because it's so easy to manipulate data. If you're doing research on a disease or something and you change your data for some reason, that's not so good. Sometimes what we call principal investigators, people who do research, who are head of the lab, they may want to get a grant and they may want you to, as a student, they may want you to maybe change your data. Is that a good thing? That's a really bad thing. So we try to train you to respect the data by writing it down in ink. That doesn't mean if you made a mistake, you can't cross it out and write what it really is. But putting white out and erasing it so that you can't see that it was ever changed is not what we do. So I just want you to keep that in mind, that we're trying to train you to be, some science professionals in a way. And that's why, we write the data in pen, we don't erase it. So you could cross it out and write. That's perfectly fine. But we don't erase it and stuff like that. Okay. So that's why we make that distinction. So I'm sorry. Sure. Yeah. Quantitative. Yeah, these are just from measurements with a ruler. Okay. So, scientists study data, and what do they look for? We love to look at data. And they look for relationships. They look for trends. They look for patterns. And they look to try to make generalizations, to try to make a general statement about something being true. Okay. And these are laws. So sometimes data leads to laws, and these are generalizations about observations. And by generalization, I just mean something that appears to always be true. Of course, you haven't done every experiment in the world. So, you could think you have a law and it's not really a law. Now, rather than talk to you about, oh wait, let me say generalizations about observations. Another thing you could say is a summary of observations that predict behavior. And I know these are words like, it's kind of hard to understand what all this means. So what I've done is put together an activity. It's activity 2. And in this activity, I'm going to give you, so you're given some measurements about the masses of hydrogen and oxygen in 3 water samples. So let's say that these 3 samples were sent off to a laboratory and they put it in an instrument, an elemental analysis instrument, and they came up, and this is what the results were. So I'd like you to read this. This goes over some of the stuff we've talked about. And take a little time to read this. I'd like you to do number 1, to see if you could come up with a conclusion based on the fact that there were these 3 samples. And when they were put in this instrument, these were the number of grams of hydrogen, and these were the masses of oxygen. Okay, so can you figure out any pattern here, any conclusion based on these numbers? Now, I know most of you probably don't have a calculator with you today, so just take out your phone. I'm sure you have a calculator on your phone, and play around with these numbers and see what you can conclude. And I will go over this. I'm going to walk around. Talk to your neighbors. If you have no idea what to do, say, hey, what are you doing on it? You know? All right, so I think a lot of you have worked this out, this big mystery here. If you take well, some people divide, well, if you divide the mass of one by the other in a given sample, in other words, hydrogen by oxygen or oxygen by hydrogen, I like to divide so I get a number that's bigger than one. So but it doesn't matter. If you did it the other way, that was perfectly fine. So 12 divided by 1.5 is actually 8. So the correct sig figs would be 8.0, but that's probably not today. Or if you take 1.36 over 0.17, you get 8. If you did it the other way, you got 0.125 for both of those. 18.4 over 2.3 is 8. So you can see that there is a constant ratio. What is a ratio? A ratio is just when you divide something by something else. There's a constant ratio of the mass of oxygen to the mass of hydrogen. Okay, so I would say here something like the ratio of the mass of O to the mass of H is always 8.0 in any water sample. Okay, so what do you think what about down here? So here we have another molecule, another compound. Carbon dioxide is another compound, and it consists of elements. And using the same type of interpretation, we can do the same thing here. Did anybody do that? Did anybody divide the 16 grams by 6 grams? And did you find what that equaled? Yes. Yeah, I would say 2.67 is, we'll learn about sig figs later, but it's 2.67. If you take the 0.32 over the 0.12, it's also the same. And of course here, and you'll notice the grams cancels. So it's 2.67. So again, the pattern here is that there is a constant ratio of mass. Which should I do? I did mass O to the mass carbon, and this ratio equals 2.67 in carbon dioxide. Okay, so we have, yes. Oh yeah, you're right. That's a gotcha. Yeah, I got to get my gotcha slips. You have to come and see me at the end of class because I think they're in there and I don't want to get them out now, but I give you, that's 2 special problem points. All right, great. All right, so now we have this observation or this law. We see a pattern for CO2, we see the pattern for water, and now we try to put that together and kind of make it general. Okay, so we have a constant ratio of the masses of each element in a compound. So, and different compounds have different ratios. But in any given compound, the elements are always present in the same proportions, okay? We learned all about proportionality in math in high school and even middle school. And so we can make this more general. See, both of these statements have the word carbon dioxide, right? Have the word water. But what can we say that we don't have to use the word water or carbon dioxide, right? We could say the elements in a given compound are always present in the same proportion and I really should add by mass, because that's what we're comparing are the masses of the elements. Okay, by the way, this video no longer exists, so you can't watch that to get any extra insight. And so this is what we call a law, right? Because this is something that's observed over and over again. And we call this law the law of definite proportions. And a lot of times it's called the law of constant proportion. So it's the same thing. The elements in a given compound are always present in the same proportion by mass. So that is, like the first step in the scientific ladder is the data. We have now the next step, which is often a law. What we do next up, is try to understand this. Okay, we try to explain this. So hypothesis is a tentative explanation of observations, which have been put into laws sometimes. Okay, now, why do I use the word tentative? Someone over there, where is she? Told me. So we try to interpret this by, we try to say, well, why this is. And the reason why we say it's tentative is because it needs to be tested by further experiments. Okay, so, I tried to come up with a tentative hypothesis. I tried to come up with one that's wrong. It's really hard to come up with something that's wrong and that makes any sense at all, because I've been doing chemistry for so long, and of course I know what the right interpretation is. So anyway, I came up with one. Here's one hypothesis. And so I could say, all right, the mass ratio of elements in a compound is always the same because only a certain amount of, say, element A can fit around element B. Right, that's my tentative explanation, which needs testing. So let me write that down. The mass ratio of elements in a compound, that's CPD compound, is always the same because only a certain amount of element A can fit around element B. So this is a hypothesis. And so now we have to test this, test it. Or you have to think about, is there an exception to this? Like, what would be a prediction? So in other words, so what would this hypothesis lead to? What would this hypothesis predict? So if it's a space issue, if element A can only fit a certain mass of element A around a certain mass of element B, then could you have two different compounds that have element A and element B? No, because only a certain amount fits. Okay, so it would predict that there is only one type of compound with the elements A and B. Okay, so, well, I actually know that we have H2O. There's another compound, H2O2. In fact, carbon dioxide, there's also CO. So the fact that there are compounds with the same two elements, H and O, but there's more than one combination that you can make means it's not a fitting issue, right? Because obviously you're fitting you know, more hydrogen around oxygen in H2O than in H2O2. So it looks like this sort of tears down the hypothesis, because there's more than one compound that you could have. So it's not a fitting issue. So that hypothesis is wrong. So it's like back to the drawing board. You have to come up with some other hypothesis. And eventually, if you get a correct hypothesis, eventually it could be that you can get a theory. And in fact, in chapter 2, we talk about the what's called Dalton's atomic theory, which is a topic of the next chapter. So I'm not going to go over it now. But the law of definite proportions is definitely explainable by the atomic theory. So the atomic theory, when we get to it, it does explain the law of definite proportions. Okay, so anyway, I want to make a plug for, many of you are you bio majors? Raise your hand. Any of you chemistry majors, physics majors? Anyway, I want to say that I encourage you to work in a lab while you are at RIC. Work in a lab and do research. It is often one of the most inspiring things that you can do in college. It's about as different from sitting in this room as listening to a lecture as it is from like watching a sport to playing a sport. I mean, it's really an amazing thing. And some students really love it and make it their career, because there are careers in scientific research, which is honestly needed now more than ever. So, you know, in biology, in chemistry, and in physics, unfortunately, our department is a little hampered right now by a lack of a building, but they should have some research space in this swing space, the temporary space. But given this, that I'm telling you this now, I also want to tell you that the physical science department has weekly department colloquia. They're Friday at 11 a.m. I'm not sure of the room. I'll tell you when I know. But this week, we have kind of an introductory thing. It's just a chance to meet people in the department. We have a kind of a meet and greet. And building 2 in the lobby. And there'll be refreshments. And I hope that you can come. This is this Friday. Okay, so go across campus and get yourself to meet some people. Maybe you can meet some fellow students there. We hope we get some people showing up. It'll be really embarrassing if nobody comes. So please come. We'll probably have pizza or something, you know. Anyway. All right. So I want to start to talk about the vocabulary of chemistry. We've done a little bit. We've done some vocabulary having to do with the scientific method. But the vocabulary of chemistry, the first thing I'd like to talk about are phases or states of matter. And these are things that, you know, these are words that you know. These are words that we use all the time. We have solid, liquid, and gas. So here we have the solid state, liquid state, and this is just an illustration of the gas state. And so what's the difference between these things? So this is like, you know, how do we organize matter? One way is to organize by state. Okay, kind of like the United States is organized by state. Well, that was a bad joke, but you could giggle a little bit, you know, throw me a bone or something, you know. Anyway, so what I say about solids is that they have their own shape. You know, you could have a rock, it has a shape. You could have a block of lead, it has a shape. Piece of aluminum foil has a shape. Particles, as you could see from this picture, are very close together. I gave you a copy of this, so you could write these notes right on it. You don't have to draw this picture. I want to save you the trouble of doing things like that. Okay, so the particles are very close together. You can see that they're right on top of each other in the picture. Lots of times you have repeating patterns. This is a very boring pattern. It's just one after the other, but you can have much more complex repeating patterns for crystalline solids. So if a solid is crystalline, it generally has a repeating pattern. Now here in the liquid, you could see that you have spaces in between, right? You have some more room to move. So what does a liquid do that a solid can't do? If you take that water bottle and you hold it, you take the cover off and you do this, it pours because these molecules are allowed to move relative to each other. So it pours, liquids pour, okay? And you can also see that the top level is horizontal for the most part. There's a meniscus, a slight dip in the middle because of attraction to the glass, but water tends to be at one level. And also you could see that it assumes the shape of the container. Okay, so that's a little bit about liquids. Gases, you could see that there is much more space between particles. In fact, gases are really mostly empty space. And because of that, a gas can be compressed. It can be pushed in. So we say that they are compressible. As you compress the gas, the particles get closer together, but you can compress it. Whereas if you try to compress a solid or a liquid, it doesn't happen. They're basically incompressible. There is simply not enough space in between the particles. So that's a big difference between different phases or states of matter. Now, when we start to write chemical reactions, we often put the phase inside a parentheses. So I might write iron, parentheses, solid, plus oxygen, parentheses, gas. So that's what we put in here, okay, when we start to write chemical reactions, which is not today. Okay, so that's one way to organize matter. But another way that chemists organize matter, and very, very important, is we do it in terms of whether the substance is pure or not pure. And this is a word that means different things in chemistry than it means in life, right? What does pure mean in life? I don't really know. Like somebody's really pure, they're sort of virginal or whatever. I don't know, but that's not what it means in chemistry. So we also organize in terms of pure versus not pure. So I really need to talk about this a little bit, okay? Because it's not something where the vocabulary of chemistry overlaps with the vocabulary of, of just spoken language. Okay. So what does pure mean to a chemist is very simple. What pure means to a chemist is that it is composed of just one type of particle. Okay. So let me give you an example. Like copper. Copper is pure. That means that it consists of only one type of particle, and that particle is a copper atom. So it consists of only atoms of copper. There's your atoms of copper. They're all lined up. A sample of copper is something like this. Okay, all copper. Here's another example. Water is a pure substance, and that means it consists of only molecules of H2O. Okay, now, do you have a question about this? Because I think that this does beg a question. What is the question? Is all water pure? And to a chemist, when I say water, I'm talking about H2O. I'm talking about pure water. Yes.
The water in our tap is
That's right. Okay. So to a chemist, when they say water, they're talking about pure water. To a non-chemist, you might say tap water. Or if you're at the beach, you might say seawater. Okay. So these are not pure. Neither is this. And that's because in tap water, you have other things. You often have some dissolved salts. You probably have fluoride because that's often added to water. You might have chlorine. You could have pollutants. Hopefully you don't have any PFAS. That's the latest thing that they talk about. Polyfluoroalkyl substances. Hopefully you not. Okay. That's actually not pure. This is a mixture, which is the next thing we're going to do. Seawater definitely has sodium chloride. Okay, probably has bits of seaweed. You know, what else does seawater have in it? Go to the beach, you get some seawater. What does it have in it? Animals in it, you bet. They're small, but they're there. Sometimes they're not so small. Okay. So there's small aquatic life. You could have microbes. There's all kinds of stuff in seawater. This is also what we call a mixture. It is not a pure substance. Now, when you talk about pure substances, like I said, there's only one formula. So it would be Cu is the formula for copper atoms. H2O, the formula for all molecules in water. So maybe you notice from this example, these two examples, that there are really two types. There are only two types of pure substances. There are compounds and there are elements. That's it. Okay. So there are only two types of pure substances. There's elements and there's compounds. Okay. The elements have just one type of atom, like copper, but you could also have like aluminum. The list goes on and on. Compounds, you could have, elements have just one type of atom. Compounds have just one type of molecule. So like H2O or NH3 or C3H8, that's propane. Okay. Now elements they can sometimes exist as more than one atom of the same type bound together. So sometimes these exist not as separated atoms, but as two or more atoms bonded together. Yes. Somebody said oxygen. Oxygen is such an example. Its formula is O2. Anybody know another one? Hydrogen is H2. Yes. These are molecules, but they are molecules that consist of two or more of the same atom. So they are samples of elements. So some elements have their smallest unit be a molecule. Okay, so I guess I should write that. So some elements naturally exist, well, have their smallest unit as a molecule. So for example, O2 is O bonded to O, H2, H bonded to H. These are examples of what we call diatomics. Diatomics, meaning two atoms bonded to form a diatomic molecule. And the elements that do this are bromine, oxygen, fluorine, iodine, nitrogen, chlorine, and hydrogen. And everybody remembers it this way. Bro-Finch, okay? And you do have to remember that the C here is Cl2, not carbon, okay? So these are the diatomic elements. So their smallest unit is a diatomic molecule, and you should know these. So you should remember these. The reason it's important is because when you write chemical reactions, if you have hydrogen is involved in a chemical reaction, it will be H2. It won't be H, because hydrogen doesn't exist as single hydrogen atoms. Same thing is true for all of these. So, you know, if you know them, it makes it very easy, or a little easier when you're writing chemical reactions to get them right, because you know the formulas have to be what the formulas actually are, and they are diatomics. Now, some elements have more than two atoms. So some elements have even more than two. In a molecule of that element. And these are not things I really expect you to remember, but sulfur, for example, exists as 8 sulfur atoms bonded together. Okay, phosphorus, P4. This has a really cool structure. It has like a phosphorus atom going to 2 others, and there's like a little pyramid here. So it's almost like with a P on every vertex. So that's a phosphorus, P4. Okay, so that's pure. Those are pure elements and compounds. So is all matter pure? No, very little is. Yes, question. Hydrogen, yeah. No, actually H2O has 2 hydrogen atoms and 1 oxygen atom per molecule. Okay, so she's asking me whether H exists just as H. And H can exist that way, but it's very short-lived. So if you took light and shined it on an H2 and put energy in it in the form of light, it'll form 2 hydrogen atoms. But they won't stay that way. They'll go back to forming H2. So it's not that it doesn't exist. It's just that in general chemistry, we generally write reactions between compounds or elements that, you know, they are naturally occurring, and it wouldn't make sense to necessarily write one with H, because that's not the way H would exist. It would immediately recombine and form H2. So yeah. I hope that answers your question. Okay, so what about those impure forms of matter? And there's a lot of impure matter, and we call these mixtures. I used that word already, but we distinguish. So mixtures are, they basically contain two or more pure substances. Okay. And when you remember when we did that exercise with compounds, water and carbon dioxide, you found that in a compound, you have a fixed ratio of the masses of the elements. In a mixture, you can have any ratio of the substances, the components of a mixture. So they contain two or more pure substances really in any proportion, which is to say it's not fixed. Okay, so in other words, you could have, say you could have oil and water, and you could have 10 grams of oil and 10 grams of water, and it would make a mixture. But you could also have oil and water where you had 100 grams of oil and 10 grams of water, and that's another mixture. And these are not a constant ratio. So that's pretty clear, I think. You can mix salt and water together in all different proportions, okay? But now there are two types of mixtures. So let me go over those. And this is the last categorization that I'll give you. So there's two types of mixtures. There's what we call a homogeneous mixture. And then there's what we call a heterogeneous or an inhomogeneous mixture. So the book calls it heterogeneous. I tend to call it inhomogeneous. These are long words, okay? But let me explain what they are. So a homogeneous mixture is where the every part, every milliliter or every, tiny little part of the mixture has the same proportion of each substance. All right, so let me talk a little bit about this. Now, normally, if I had my lab, I would have brought some demo materials, but I don't have my lab, so I can't do that. So let's say we have some sodium chloride. So here's some salt. And we have a Erlenmeyer flask with some H2O in it. Okay. And we add these together and we mix them. And you shake it up. And then you leave it. What does it look like? You must have done this at some point. You take salt and put it in water. And then you put that on the table. What does it look like? Sorry? Actually, it doesn't look cloudy. After a while, what does it look like? It dissolves, right? We're using all these terms, but it looks clear. It looks just like water. You can't tell that there's sodium chloride in it. Okay. It might look cloudy initially before it dissolves, but it does clear up. Okay. So if it looks totally clear. It looks just like water. Looks the same. You can't see the sodium chloride in there. Okay. If I look at this part of the mixture, and then I look at this part and I analyze these two different parts of the mixture. If I took a little drop out of one section of it and a little drop out of the other, they would have the same saltiness. They have the same proportion of salt and water within that mixture. Okay, so you have the same amount, I should say the same relative amount of NaCl and H2O in every part of this mixture. That's why we call it homogeneous, because this homo means same in Greek. Okay, so that's a homogeneous mixture. And most of the time, I don't call things homogeneous mixtures. Anybody know the term we use in chemistry for a homogeneous mixture? Yes, a homogeneous mixture is called a solution. And that's what the word that I will use. It forms a solution. And what it means is that those sodium chloride particles have become evenly dispersed in the water. And I'll show you a picture of that in a few minutes. Okay, so let me now illustrate to you what a heterogeneous mixture is. Okay, so let's suppose I take a solid, another solid. Oops. No, go away. So here's another solid. This is calcium carbonate. It's a white powder. Okay, I take that white powder and I dissolve it, or I'm not going to be able to dissolve it. I put it in water. And now I mix this. Well, it's a solid, so it's not really like oil. It's the same idea. What happens is it looks cloudy. So this is where you see cloudiness. So cloudiness is evidence of an inhomogeneous mixture. That's where something doesn't dissolve. Now, calcium carbonate is actually like ground up chalk. If you try to dissolve chalk in water, it really doesn't dissolve very well. So if you let it sit, what you will have, terrible artist, it's really sad, is you will have the calcium carbonate on the bottom. And then you will have it be clear on top if you let it sit. So if you took a sample from here, you took a drop, you take a sample from there, it's going to be mostly H2O. And if you take a sample from here, it's going to be mostly calcium carbonate. So that means it does not have the same composition throughout. Okay, does that make sense? So that's the big difference between homogeneous and inhomogeneous. Okay. And you could think about this word composition here. That's like it doesn't have the same percent water and percent calcium carbonate. That's what I mean by composition. The amount of each of the substances. It's very different throughout in an inhomogeneous mixture. And here's a picture that's from the book, and it talks about how matter is divided into pure and not pure states. Pure and not pure substances, sorry, that's what I meant. Pure, you've got your elements and your compounds. Everything else is called a mixture. You've got your heterogeneous, which I call also inhomogeneous, and your homogeneous, which is a solution. And it gives you some examples here, okay? So like helium in a helium balloon is an element. You have all helium atoms. All one type of particle, the helium atom. In pure water, you have all H2Os. And now this is showing wet sand, which you have in black and white, so it's very hard to see what's going on here.
But you could see that in wet sand, you have part that's mostly water. And then here you have mostly sand. And sand, by the way, is mostly silicon dioxide. So you're seeing that gray atom here is silicon, and each has 2 red oxygens on it, just like the red is oxygen and each has 2 white hydrogens on it. And here what this is attempting to show you is molecules in tea. You see the water molecules floating around, and you've got these sugar molecules, and of course there are other molecules in there, but they're all evenly dispersed. So this is a solution. You could tell because it looks clear, just like when you dissolve sodium chloride in water and mix it up, it looks clear. If you drop food coloring in water and you mix it up, even though it might look a little red, it's still clear. And that indicates evenly dispersed. Yeah, but that's not a solution. The milk is a solution. Well, the milk is an emulsion. That's complicated. But the chocolate chips, they're not going to evenly distribute unless you have like maybe one of those dissolvable powders, or that's not really quite the same. Anyway, let's do some examples, seeing as we're talking about examples. So I have this activity 3. We don't have much time. Oh my God. Well, I'd just like you to do, how about, yeah, let me, so the reason I'm like ha-ha-haing is because I put down these as a handout of the day. Okay, so I want you to be able to do that before you go. So let's just do these together. Chicken noodle soup. Is that, okay, so we want to know, is it a compound, an element, a homogeneous mixture, or a heterogeneous mixture? Chicken noodle soup. That's a heterogeneous mixture, absolutely. Sucrose. Yeah, look, I gave you the formula. So that means it's a compound, right? Because I've given you the formula. And we see sucrose, we assume it's pure, that's a compound. What about if you prepared lemonade? So I'm talking about if you take a powder and you mix it in with the water, you shake it up, and so it looks slightly yellow, but it's all looks very uniform. Homogeneous mixture or a solution. Yes. What about your pulpy orange juice? Yeah, because the pulp doesn't get evenly dispersed. It's not the same throughout. All right, now sand, let me modify this and say beach sand. Okay, beach sand. So what? Yeah, that's like a heterogeneous, but what else is in there? We have silicon dioxide, which is what sand is mostly made out of. But what else have you got in there? Is salt in there? There's some water in there, but let's say it's dried up. Maybe you have some shells in there. You have some dead animals in there, whatever. I don't need to get too illustrative about it. All right, copper wire. What's that? Copper is an element, right? So it's an element. Consists only of copper atoms. All right, now here, rust, iron oxide. That is a compound. I'm going to give you the formula, Fe2O3. Okay. Calcium carbonate that I talked about here, I'm giving you a formula. What does that mean it is? Compound. Is this people in the back getting along with this too? Good. All right, now here's rubbing alcohol. So I have the label here. I'm going to blow it up. So this one, it says isopropyl alcohol, 70% by volume. What's the rest of it? Inactive ingredient, purified water, right? But when you look at rubbing alcohol, it looks clear. That isopropyl alcohol has been dispersed completely in the water. So it's 70% isopropyl alcohol in water. It is a solution. Okay, so now, so this is a handout of the day. So I'd like you to quickly, in the next 3 minutes, do these. I don't know, whatever's on the HOD handout. I don't know what it is. I don't remember where I put there. Oh, the bottom part you can't. We didn't do that yet. So just do 10 to 16. And you're allowed to ask me questions about it. So what about oxygen? I'm just going to go over this. This is our first one. I don't want anybody to be stressed out today. What's your question, by the way? Can you speak up a little? No, it's one or the other. Yeah, seawater is heterogeneous because it has all those other things in it. I didn't say salt water, right? Yeah, this is heterogeneous because, you know, it's got seaweed, it's got animals. Yeah, it's not homogeneous. Oxygen, what's that? Element. Now, here I tell you, vinegar is a solution of acetic acid in water. So what does that mean? White vinegar is totally clear. Yes, but we would here on this assignment, we'd say homogeneous because it is a solution. What about if you mixed oil and white vinegar? Shake it up. What happens? What does it look like when you're shaking it? Cloudy, right? Then you let it sit and it separates. What's that? Yeah. What about if you mix water with vinegar? Well, vinegar already has water in it. So it says vinegar is acetic acid and water. So we know that forms a solution. So adding more water just makes it a less concentrated solution. So a solution is homogeneous, right? So that's homogeneous. And what about air? Yeah. It's just all dispersed evenly in the air. So you can have a solution in the gas phase as well. All right, thank you for coming today. Go to the lab today is in Craig Lee 213, and Dr. Lung is there. Dr. Knowlton will be there tomorrow. Anyway, I'll see you Thursday. Oh, the handout of the day you have to hand in before you go. Yes. So just put it here. You just want one piece of paper. Get the handout, come get it. Make sure your name is on it.